In this video, we're going to be reviewing work, energy, and power. This is Unit 3 of AP Physics 1. We're going to begin with the concept of work. Work is the transfer of energy due to a force applied to an object, causing displacement in the direction of the force. And work is a scalar. It only has a magnitude, no direction. The equation for work is force times the displacement times cosine theta. The unit for work is joules, and a joule is equal to a Newton meter. Now let's take a look at examples where work is positive, negative, or zero. So if the force is in the same direction as the displacement, then the work is going to be positive. If the force and the displacement are in opposite directions, then the work will be negative. If the force and the displacement are at an angle, then we will need to use our equation. Force equals Fd cosine theta. Theta will be the angle between the force and the displacement. If the force and the displacement are perpendicular, then the theta is going to be 90 degrees, and cosine 90 degrees is 0, so the work done will be 0. So why do we care if work is positive or negative or 0? Well, work tells us the transfer of energy going into or out of a system. So a positive work means energy is transferred into the system, and negative work means energy is transferred out of the system. We'll see more of the significance of this later as we talk about energy. On a force versus displacement graph, the area under the curve represents the work. When I say area under the curve, I mean the area between the graph and the horizontal axis. This area can be positive or it can be negative. If I wanted to find the net work, I need to take into account the positive and the negative section of this graph. Work can be done by conservative forces or non-conservative forces. So we're going to take a moment to compare these two. Work done by a conservative force is path independent. So here's an example. So here I have a green box that I'm going to lift up. And we're going to focus on gravity force because gravity force is an example of a conservative force. So we're going to lift it up. Gravity force will be doing negative work because the object is moving up while gravity force is pushing it down. So the directions are opposite, so the work is negative. Then I'm going to move the box to the left because the force and displacement are perpendicular. The work done by gravity is 0. Then I'm going to move the box down, and the work here is positive because the force and the displacement are in the same direction. Now, whether I move the box up to the left and down, or if I move the box directly to the left, the total amount of work is going to be the same. In this case, it's going to be 0. So we say that it's path independent. And furthermore, if I move the box up, left, down, and back to the right, back to its initial state, we call this a closed loop. The net work done on the object is going to be 0, the net work done by the gravity force. Another example of a conservative force would be a spring force. Now let's contrast this to work done by a non-conservative force. So example of non-conservative force would be something like friction or air drag. So here I have my green box and it's on a table, and a work done by a non-conservative force is path dependent. So let's say I were to push this green box up forward here to the right and back down over here. That amount of work done by friction is different than if I had taken the box and moved it to the right. So we say that it's path dependent. And if I were to move this up, right, down, and back to the left on the table, back to its initial state, we refer to this as a closed loop. The work would not equal to 0, so it would be a non-zero amount of work. Next, we're going to take a look at energy. So energy is the ability to do work. And energy is a scalar, which means that it has a magnitude but no direction. The unit for energy is joules, and there are different forms of energy. I like to think of these as different ways that energies are stored. So for example, with gravitational potential energy, this is energy that's stored in the gravitational field, and this only occurs when there's more than one object. So with gravitational potential energy, we're looking at the object Earth system, and the equation for gravitational potential energy is mgh. This is when the object is near the Earth's surface. Once again, it assumes that the Earth is in your system, and we're assuming a constant gravitational field. Next, we have kinetic energy, and kinetic energy is energy stored in the motion of the object. and it's equal to 1 over 2 times the mass times the speed squared. And this depends on your reference frame, because if you were to observe something moving, it depends on where you're observing it from. If you see a car driving by at 60 miles per hour, you observe that speed. But if you're in the car, you observe that the car is moving at 0 miles per hour because you're moving with the car. So kinetic energy does depend on your reference frame. The next, we're going to take a look at energy stored in a spring. So this is a spring or elastic potential energy, and it's equal to 1 over 2 K. K is the spring constant times delta X squared. So the delta X is the distance the spring has been stretched or compressed from the equilibrium position. Next, we have the rotational kinetic energy. This is energy stored in the rotational motion of an object, and it's equal to 1 over 2 times the rotational inertia, or the moment of inertia, times the angular velocity squared. And then lastly, we have the gravitational potential energy. This is the more general equation. So let's say you're not on the surface, you're further away, and it's equal to negative big G, the gravitational constant, times m1 times m2 over r. M1 will generally be a large mass, such as a planet, and the other mass will be a smaller mass object. Mechanical energy refers to potential and kinetic energy. By the way, potential energy sometimes we'll use a symbol capital U, and for kinetic energy sometimes we'll use the symbol capital K. Mechanical energy is conserved when only forces doing work on the system are conservative forces. Examples of conservative forces are gravitational force and spring force. Just a quick reminder of non-conservative forces. Those would be forces like friction or air drag or applied forces. And that's because these forces will transfer some of those energy into heat and sound energy. Now, when we talk about conservation in physics, we're saying that it doesn't change. So mechanical energy, we're talking about how the initial total mechanical energy is equal to the total final mechanical energy if only the forces doing work on the system are conservative forces. We can represent it with this equation here, that the potential energy plus the kinetic energy is constant. Now, the potential energy could change, the kinetic energy could change, but the total amount is constant. We can also write it as Ui plus Ki equals Uf plus Kf. Let's take a look at some examples. Here's a pendulum. I'm pulling to the left and I let it go, and it's falling. The potential energy, the gravitational potential energy is decreasing, but the kinetic energy is increasing, but the total amount of mechanical energy stays constant. Here we have an apple. We're dropping the apple as it falls. The gravitational potential energy decreases, but the kinetic energy increases, but the total mechanical energy, once again, is constant. Here we have a block on a spring. If we pull it to the right and we let go, it's going to start to, it has elastic potential energy. It's going to move to the left, and that elastic potential energy is going to decrease, but the kinetic energy is going to increase. So once again, the total mechanical energy is constant. Internal energy is heat energy that causes an increase in the temperature of the system. An example of this is work done by friction. And we can calculate work done by friction by taking the force of friction times d, the displacement, times cosine theta. So here's an example. I have a block here that's moving to the right. So maybe I pushed it initially, but now it's not being pushed by my hand. It's just slowing down on the surface because it's on a rough surface, and it's moving to the right. However, friction is to the left, and theta is going to be 180 degrees because it's measuring from the frictional force to the displacement, and cosine 180 degrees is -1. So work done by friction is going to be negative. The significance of this negative is telling us that it's removing energy from the system. And although mechanical energy is not conserved, we can still use the work energy principle when we're dealing with work done by non-conservative forces. Ui, the initial potential energy, plus Ki, the initial kinetic energy, plus the work done by the non-conservative force, in this case it's friction, is equal to the potential energy final plus the kinetic energy final. Next, we're going to look at the general equation for gravitational potential energy. The reason we wouldn't just use mgh is because as you move further and further from the Earth, g is no longer 9.8, and the gravitational field is not constant. And so instead, we have to use this general equation for GPE, which is negative big G, which is the gravitational constant, times m1 times m2 divided by r. One of the masses will be a mass of a large mass, like a planet, and then the other object will be a much smaller mass. Here we have a graph representing this relationship. We have gravitational potential energy versus the distance of the object as you move away from the surface of the planet. Here RE is the radius of the Earth, and as you move further and further away from the Earth, you'll notice that the gravitational potential energy increases. Although it doesn't increase in magnitude, it increases in that it becomes less and less negative. So as the distance increases, gravitational potential energy increases, it becomes less negative. Also, the gravitational potential energy is equal to 0 as r approaches infinity, and only changes in gravitational potential energy matter in solving most problems. You may have noticed that there's a negative sign in front of the equation, and that negative sign indicates that energy is required to separate masses to infinity. And without that energy, the mass would just fall back to the planet. So now we're going to try to connect the concept of work and energy through what's called the work-energy theorem. And this states that the net work done on an object is equal to its change in kinetic energy. So the work net equals to delta KE, which is equal to the final kinetic energy minus the initial kinetic energy. And we know that kinetic energy is equal to 1 over 2 mv squared, so we can write it as the work net equals to 1 over 2 mv final squared minus 1 over 2 mv initial squared. When the net work done is greater than 0, this means that the kinetic energy is going to increase and the speed of the object will increase as well. When the net work is less than 0, that means the kinetic energy will decrease and the speed will decrease. If the net work is equal to 0, then the kinetic energy and the speed will be constant. Now we're going to apply what we've learned about energy and work to orbits. We're going to start by looking at circular orbits. Here we have a satellite orbiting the Earth, and you'll notice that the satellite is moving in a direction perpendicular to the gravitational force. So the displacement of the satellite and the force acting on the satellite are perpendicular, so the work done is going to be 0. Since the work done is 0, the work energy theorem tells us that the kinetic energy is not going to change. So the kinetic energy is going to be constant. Since the kinetic energy is constant, the speed of the satellite is also constant. The gravitational potential energy is also going to be constant because the orbital radius is constant. Now, since only conservative forces are acting on our system here, the total mechanical energy is constant, which means that the sum of the kinetic energy plus the gravitational potential energy is going to be constant. Because that there are no external forces doing work, no energy is added or removed from the system. Now we're going to take a look at elliptical orbits. And here we have a satellite going around the Earth. And we're going to start with the position on the left here. And the green dot represents the satellite. It's moving in this direction. And there's a gravitational force towards the Earth. And you can see that there is a component of the gravitational force that is in the opposite direction of velocity. That means that the gravitational force, that component, is doing negative work on the satellite, which means that the kinetic energy of the satellite is decreasing, which means that the speed of the satellite is decreasing. And so we say that the kinetic energy is not constant and that the speed changes. On the right-hand side of our orbit here, the satellite is moving this direction, gravitational force is this direction. And you can see that there's a component of the gravitational force in the direction of the velocity. And so at this point, there is positive work done on the satellite by this gravitational force. And this positive work is going to cause the kinetic energy of the satellite to increase. And so if the kinetic energy of the satellite increases, that means the speed of the satellite also increases. Gravitational potential energy is not constant because the orbital radius of the satellite and of the satellite's orbit is changing, and the total mechanical energy, Gp plus Ke, is constant because only conservative gravitational forces are acting on the satellite. Escape velocity is the minimum speed required to escape a planet's gravitational pull. In this diagram here, we have a planet. Let's say this is Earth, and we have a green dot. Let's say this is a baseball. And we were to toss the baseball up into the air, you know that the ball would fall right back down. But imagine if you could build a robot that could throw a baseball super fast. The question is, how fast would this robot have to throw the ball into the air so that it doesn't get pulled back towards the Earth? And we're assuming no additional forces, so there's no propulsion on the baseball and that there's no air resistance. To calculate the escape velocity, we can set the total mechanical energy equal to 0. And the gravitational potential energy is negative big G times the mass of the planet times the mass of the baseball divided by the distance between the baseball and the center of the planet, plus 1 over 2 times mv squared. Set that to equal to 0. You'll notice that the masses will cancel. The v squared will equal to, if I multiply 2 on both sides, I get 2 big G times big M divided by R, square root on both sides. We get that the escape velocity is equal to the square root 2 times the gravitational constant times the mass of the planet divided by R, the distance between the ball and the center of the planet. Power is the rate at which work is done. To calculate average power, we can take the work done divided by the time. Since work is related to the change in energy, the average power is equal to delta E over T. The unit for power is watts, and a watt is equal to a joule divided by a second. We can also calculate power by substituting the equation for work, which is FD cosine theta divided by T, and we know that D divided by T is speed. We're going to use V to represent speed here. So the instantaneous power is equal to the force times the speed of the object times cosine theta. When solving energy problems, it's helpful to use an LOL energy chart. Here we have a block of 5 kilograms sliding down a ramp which is 3 meters long, and we want to find out what the velocity of the block is at the bottom of the ramp. So first we're just going to qualitatively represent this, and then next we're going to mathematically solve it. So initially it has only gravitational potential energy. And this circle represents the system that we're working with, which is the block and the ramp and the earth. And as it's sliding down, because of friction, some of this energy is transferred out of the system. And at the bottom of the ramp, we have some kinetic energy. Notice that the initial part has 3 blocks, and then the final has 2 blocks, and that's because 1 block of energy was transferred out. Now, this is not going to be completely mathematically accurate. It's just qualitatively helping us to set up the problem and understand what's going on. That you start off with gravitational potential energy. Some of that energy gets converted into heat and transferred out of the system. And then at the end, we have some kinetic energy, but that kinetic energy is less than the gravitational potential energy that we started with. Now we're going to mathematically solve this problem. So this block is going to slide down the ramp, and we want to find out what is the final velocity of this block. We're going to need to know the height of this ramp, and we can use trig to solve that. Sine 30 equals opposite, which is h, divided by the hypotenuse, which is 3 meters. H is 3 times sine 30 degrees, which is 1.5 meters. Next, we're going to need to know the initial gravitational potential energy, which is equal to mgh. The mass is 5 kilograms, g is 9.8, the height is 1.5, which we just solved. The gravitational potential energy initially is 73.5 joule. The kinetic friction is equal to mu times n. And here we have a force diagram. We have mg going straight down. Normal force is perpendicular to the ramp. You can see that there is a component of mg that is along the same axis of the normal force. And so the normal force is equal to mu mg cosine theta. So I can substitute that in here. The reason I know that normal force is equal to mg cosine theta is because it's not accelerating along that axis. And we can calculate that and we get 8.48 newtons. Now we can use our conservation of energy equation. Initial kinetic energy plus the initial gravitational potential energy plus the work done by friction is equal to the final kinetic energy plus the final gravitational potential energy. We're going to substitute our numbers that we've calculated. So the initial kinetic energy is 0. The initial gravitational potential energy is 73.5 joules. The work done by friction is negative 25.4, and we calculated that here, which is because work is force times displacement. We have the force of friction times the displacement, and it's negative because the friction and displacement are in the opposite direction, so we have a negative number here. The kinetic friction, the final kinetic friction, we're solving for that, and the gravitational potential energy at the bottom of the ramp is going to be 0. And solving for VF, we get VF squared is equal to 19.2, square root both sides, we get that VF is equal to 4.39 meters per second.